Atomic and molecular orbitals are very important in organic chemistry. We're interested in knowing the position of the orbitals and geometry, and sometimes that has an outcome that's important for things in chemical reactions. So we're going to have to get theoretical here for just a second. And let's talk about atomic orbitals. So they're defined by a special mathematical function called a wave function. So unless you're a chemistry major or Chem E major, you're probably not going to see this outside of our class again. Now that wave function, our psi here, that's a mathematical description of the size, the shape, and the orientation of an orbital. Now as far as the wave function is concerned, the amplitude may be positive or negative, or it could be zero. And if it's zero, then we call that a node. We're going to get a positive kind of solution to the wave function, and we're going to get a negative solution to the wave function. But that doesn't indicate charge. They're just the mathematical solutions. And the wave function relates energy of an electron to a specific location. All right, as far as quantum chemistry goes, if we take the wave function and we square it, it gives us the probability of finding an electron at a certain location. And each of these wave functions, they're orbitals, so they can hold a maximum of 2 electrons. All right, so that's really the extent of what we want you to know for wave functions. And again, if you're a chemistry major, you go on, you'll spend a whole quarter or longer studying wave functions. So let's take a look at S and the p orbital. So we're not going to look at the d or the f here. So the s orbital is spherical. So we typically draw it out so that it kind of looks like this, right? It's a circle. You got a nucleus in the middle, and there's a plus answer to our wave function and a minus answer. If we plot it out on an xy axis, it looks kind of like this. So here in the center, you have your nucleus here. And this is your wave function solution right here. And as we go off to the right, moving this way, you are going farther and farther from the nucleus. So that's your positive answer. And then down below, you have your negative answer to the wave function of the s orbital. We don't usually draw them out like this when we're talking about orbitals. We draw them with circles and a positive answer here or a negative answer. And if we take the square, then that tells us the probability of finding an electron there. So it just takes the negative part of your wave function and flops it up to the top there. Okay, so the take-home message here, know the basic shape of the mathematical solution and also know how we represent it with these circles and a plus and a minus. Okay, now the p orbital it's like a guitar string in a lot of ways. If you take your finger and you put it exactly halfway on the guitar and pluck it, you'll have part of the string going up in one phase and part going down, essentially. So we get 2 solutions to the p orbital wave function. You end up getting this plus and this minus. Right, so you're positive on this side and you're negative over here, or you're positive on the left and you're negative down below. Okay, and then notice in the middle, here's your nucleus, just like we saw before. But this position right here is a nodal plane. So that's a spot where you're not going to find an electron. Now, what we typically do is we don't draw them like this, just like the s, we don't draw it like a mountain, we draw it like a circle. So the p orbitals we usually draw as these kind of bilobal orbitals. So here's our node right here in the middle. This is our nodal plane. And we have a positive lobe and a minus lobe and a plus lobe on this side and a minus lobe on that side. So we get these 2 lobes here. Okay. Now, what happens when we add these together? That's what we really want to do. How do we form bonds? And this brings us to our next section, which is called linear combination of atomic orbitals, or LCAO. So these atomic orbitals can combine and overlap to give more complex standing waves, more complex wave functions. Adding or subtracting the wave functions to give new wave functions of new orbitals is called LCAO. Now, one thing to point out is when we add these together, the new orbitals generated always equals the number of starting orbitals that we started off with. So in other words, if you add an S and an S, that's 2 starting orbitals, you're going to end up with 2 in the end. So you have to conserve the number of orbitals in your addition here. All right, so we're going to look at a couple things. First, when orbitals on different atoms interact, they can produce molecular orbitals. Right, so we'll look at that. It leads to bonding or anti-bonding interactions. And then when orbitals add on the same atom, they give hybrid atomic orbitals. So it's the same atom or different atoms. Okay, and some of these models we use in certain cases more than others. So when we talk about spectroscopy, we often talk about molecular orbitals. When we talk about bond atom shape and stuff, we usually talk about hybrid atomic orbitals. So they're both models that work depending on what situation we want to use them in. So let's take a look at H2, guys. So this is what H2 would look like. So of course, hydrogen is a 1s1, right? So you have a single electron in the 1s orbital right here. And we're going to represent that by putting an arrow up, half arrow up, just like that. Right? And we're going to have another atom over here of hydrogen with its 1s1 electron. All right. And over on this side here, these orbitals here are on the H atom. So this is just a single H atom. And down here below is what happens when we add these things together. This is what's giving us our molecular orbitals. So if we add them and they end up being in the same phase, then they add together constructively, and we get a sigma bonding molecular orbital. So I tried to display that by putting them in the, basically as the same color here. So this would be constructive overlap. Remember, for the S, if we talk about the S orbital, we have a positive and we have a negative. So down here for constructive, it's a positive added to another positive, or it could be a negative added to another negative. All right, so if we add them out of phase, that would be a plus and a minus, we get a destructive or deconstructive overlap. So up here at the top, we have deconstructive overlap. And notice here, by the way, that we're starting off at our ground state right here. So this is our ground state, right? That, in other words, that's the energy of just the s orbital of the hydrogen atom. And then when we add them together, we get stabilized by some amount of energy, and we get destabilized by some amount of energy. Now in the end, to figure out if this is something that's favorable that might occur, we put the 2 electrons in and we get this. So the 2 electrons are in a lower energy, right? They've been lowered down by this amount of energy, and that's why it's a favorable thing for these 2 things to come together. Now, if this happened to be 2 sets of electrons, so in other words, just as a side note here, like what about He2? So He has an S with 2 electrons in it, and another S with 2 electrons in it. We get constructive, deconstructive overlap, and then we put our electrons in here, and we put them in here. So overall, the net energy, there's no net perfect stabilization because we're stabilized by some value, we'll call it X, and then we're destabilized by some value, we'll call it minus X, right? So the overall energy of forming a new set of bonds between 2 heliums by itself is not that favorable, so we don't expect diatomic helium to really form, right? Where H2 over here, we have electrons occupying only this lower molecular orbital. Now, to make things even more complex, we have other types of sigma bonds that can form. So we have the overlap between s and p's. So we saw the overlap between two s orbitals, but we can have an s and a p overlap. Now, there's a couple different choices for that. So you can have your bonding molecular orbital and your anti-bonding molecular orbital. So here, remember, we're adding in phase, so you get your plus added to the positive s orbital, and then a minus s orbital. And it leads to, again, your sigma bonding and your sigma star anti-bonding. Now, as far as constructing something like this will be something that you can consult. It's not expected right now that you memorize all of this. But it's important to know that we can get sigma bonds from an s overlap with a px orbital. Now down here below, letter C, this is the other way we can get a sigma bond forming. It's from the head-on overlap of p orbitals. So again, we get this sigma bonding, and we get this sigma anti-bonding with a node. So the deconstructive overlap results in there being a node that's present. Now, the one that you do need to be familiar with here is pi bonding. So we want to have this sideways overlap. And again, we can have this deconstructive overlap here, where we have a blue and a green, opposite colors or different colors kind of lined up. Or we could look at the sign, a plus and a minus. Or we can have constructive where the same color or the same sign. And that gives us pi anti-bonding and pi bonding. And the way that we typically draw this is we usually take a molecule and put it on its side, and it would kind of look like this. So here's your pi bond, and then one of those is a sigma bond. It's a single bond. So if we take this and kind of rotate it on its side, we can see our p orbital lined up like this. So this top lobe is just 1/2 of your pi bond, and the other half down here below is the other half of your pi bond. So they add up to giving you 1 pi bond.